Better? Yeah.
Yep, that's fine.
Okay, so I was thinking for a while about how to open and describe this, and let's try what I saw today on my way here. A decade ago, the entire world, when you saw the word bridge, you saw a catenary device that it was basically indistinguishable from Galloping Gertie, the Brooklyn Bridge, and the Golden Gate Bridge. Sometime around 2010, that changed. And it changed dramatically. And it changed to where we ended up with these single stage, much more elegant, much lighter, much better bridges. And I spent a bunch of time today trying to figure out why. And it turns out that it was all three. And you'll see our case isn't that dramatic, but it was materials. We got a little bit better steel. It was manufacturing that allowed you to simultaneously pull two things apart from each other and therefore build cable stays. And it was analysis. What we are trying to do is solve the following problem that has been stated better, unfortunately, in the RISC V world. The cost of the boom processor in terms of people hours was primarily building the register file. Register files are a black art that you build this cell out of ground rule compatible rules, and it has as many ports as you negotiate the first day, and after that it becomes a very complicated thing, and you basically are stuck with that world. We are trying to export that world up a level to go from what fabs had been working a long time on, which is the 6 transistor world, to a 10 transistor unit that separates reads and writes, and therefore allows you to get much faster, much more voltage scalable items. And from there on up, it is our plan to replicate and add more ports. So similarly, we expect to go from a world where everybody's reg file, including one I designed about 15 years ago, are these gargantuan cell devices that are different for each one, to a much more uniform thing where the fabs compete and work with you to build a bigger cell, to build a specific cell, and you just replicate from there. Or not to carry it a little better, we're trying to be IKEA and tell the bolt people to build a little better bolt to build many more devices. And that's what the goal of getting 100+ nanometer, 130 nanometer version of this out in the public domain is. Now let's talk about the 3 features of this Toy-SRAM, and let's make it clear. My name is Montoye, and it's a toy that it makes it all simplified. So the custom core that we've gotten some progress on internally and trying to build consists of a 10 transistor SRAM. On that word, we will describe that once you go from separating reads and writes in 8 or 10 or more transistors, you have something that is more robust than reading and writing in the same port. And it's associated, well-tuned, hand-placed decoders from a standard library, and we are trying to make that library, we're trying to make it so that you can easily grab any library and have basically the right characteristics. We chose 64 regs as a good standardized number that we could do with one big dynamic stage and one little and a static and a little dynamic stage. We went down to 24 elements. We went to a very small number of elements so that we could have our RCs, so we could control. Essentially, the idea here is to take a bunch of experienced guys and say, let's get the black art out of the problem and let's make it simple. And we have at least produced some prototype of a version that is this very small item. Okay, 64 regs, 24 bits. And it's a lot smaller than other attempts at this because we carefully organized the parts of it and partitioned it between this custom unit and what is in this next statement, a CAD-friendly wrapper. What I mean by a wrapper is the thing that has all of the latches, all of the storage elements that aren't in a reg file, all of the clocking system, and all of the muxing, and a little logic within it. This allows us to control this custom block well, and allows us to run at pretty high speeds so that we can talk about multi-clocks per cycle, which we'd done a bunch of years ago for write, and we're now looking at doing for both read and write. The third item is the one that really makes it reduce labor. Historically, people had done quite a bit of work on expanding read ports by writing into multiple places and reading out locally. There is a symmetrical solution that allows you to write locally, retain the presence information, and this has been done for FPGAs before, and that allows you to expand your read ports and your write ports. Once you can expand reads and writes, we basically are now returning the problem to where the architect can pick with little extra negotiation other than the raw area. That is not, oh my God, I just asked him to add a port, he can't do it at this point. So this allows these three things. One gives you a basic cell, two gives you a cell that you might be able to clock twice as fast read and write, and this third one gives you the ability to add as many ports as you want within the system. Now I'm going to go into something that's related to this that I want people to attempt to consider. Oh, that was bad. Historically, people have focused on bit density above all. The fabs have focused on bit density above all. That has a problem in that the architect wants bandwidth as well as bit density. And I'm using this term specific bandwidth with an homage to Archimedes getting into the tub and talking about specific gravity. That is, what is the band, how much area does it take to get a certain amount of bandwidth for a certain size array? And we should always think in terms of that, because architects want specific bandwidth for specific bandwidth, and they get high density and have to build their own ad hoc buffering below it. the goal of building this item is to produce a new level of high specific bandwidth by having this 2 read, 1 write, 10 transistor SRAM that we can run at about twice the clocks of most people's normal 25-ish FO4 machine. And above that, do it through replication. This is okay. Now, what we would like to build is a first single read, single write version with some sort of synthesis on BIST to validate what we've got. Then we want to, and will we get there in this presentation? We want to reclock this structure in such a way that we can get 2 reads and 2 writes out of each of those cells per half cycle, or we want to get 2 times a one write, 2 reads per half cycle, or 4 reads, 2 writes per full cycle. This is the limit of, and I go back of the previous discussion. This is the limit of where we go on item 2 here, before we go to item 3 to add still more ports. This picture goes through our approximate organization. One of the reasons we went to such narrow bit width was we attempted to align the decoder with the cell. And that means you only had a certain number, 4 transistor sites to drive up and down. By organizing items in the manner you are seeing, that is putting the decoders aligned with the cells, putting the bit positions aligned with the cells, and using the available spacings among the available spacings that are left to put some of the pre-decode. We are organizing this in as dense a manner as we know how. Now let's step down a level and spend a little time on the cell itself. The first thing to recognize is that when you build a SRAM that has segregated reads and write ports, that is, if we look at this picture, the writes go here, the writes go in the center, attached to here and here, and the reads come out. Once you segregate it, it has been shown a lot of times that you can run the voltages much lower. In fact, well over a decade ago in 65 nanometer, we were down to 0.4 volts. Secondly, in parallel with that activity, you can run it a lot faster because you don't have to do any other than aligning a small number of edges. You are separating the read and write activities. It is my hope, and that was the introduction, that this type of structure can be optimized at the fab level in ways that are fundamentally better than just being at ground rule minimum. Just being at general ground rule minimum. If you just do a modest search, you will see the world is full of ground rule waivers for 6 transistor SRAMs. We would encourage the fabs to do some work to optimize this item because it is voltage scalable. What that means is this will run way below 0.5 volt. And when we're in a modern era of ultra high density, you got to get down there to really be able to utilize these ultra large chips. When we first talked about these low voltages, it was interesting, but this year at Hot Chips, Esperanto talked about a 0.4 volt chip. This type of technology where you're separating the read and write port is required to go to the ultra low voltage space. And as we pile up past the 10 nanometer-ish realm, there's going to be more and more chips that want to run at these ultra low voltages. Sorry to jump around, but now we're going back to what I meant when I talked about composing items. And the problem is I want a 4 read, 2 write register file. But the basic cell structure is 2 read, 1 write. In the left corner, I just have 4 copies of it. I replicate for read by just sending the output to both sides. And picking off the 4 reads, 1, 2, 3, 4, R01 and R23. Writing is done in a symmetrical but opposite manner. That is the register file, that is, you write into separate copies. Remember the most recently used register, and read both copies out and take the one that was most recently used. If I'm capable of double data rating the write, which is what we had done a decade ago, then I only need 2 copies to produce more reads. If I can double data write the read and the write, I can get myself a radical gain in aerial efficiency, while the second half of the reads come a half a cycle later. God, it's okay. Again, the hope is to work with Jim Stein at Oklahoma State to build 130 with 5 layers of metal. It would be nice to build it with these low layers of metal. If provided, we'd like to build one in 14. And the best case would be that this 5-layer of metal designed item would enable someone like the company I work to produce their 2 nanometer stuff, which doesn't have a full back end. Truth to the world, the 4 nanometer does, the 2 does not, and have an easy way to show voltage scalability. So let's go and review what we have, and then we can have hopefully some time for some spirited questioning. We have built in an aggressive process and want to move into this 130, a dense item that uses mostly standard cells with only a couple of exceptions, and the 10T cell. It turns out that there's a total of 3 cells that aren't standard for a library to do this. And I'm trying to use the basic rules I understand of how standard cells work to make this something that should be essentially pick and play over a variety of technologies. Above that, you have a standard piece of VHDL or Verilog that wraps it with the latches that drive it, the clocking system, and a second and a small portion of the decoding. And includes the ability to clock at these double data rates through building your own pulses. Above that, when you need additional ports, you have an algorithm that allows you to expand. And yes, there's some linear area growth, but this allows you to, so this allows the architect to have what they want, which is the ports they envision in the architecture, as opposed to what they negotiated for the first week of the design. We believe this type of system can replace many existing register files and is very labor efficient and takes the black art away from another part of VLSI design, making it an ideal component for the open source world. Thank you. I'm going to reserve the rest of the time for any questioning. Because I think the rest of this is too much detail.
Thanks, Bob. It's Anton here.
Sure.
Yeah, I'm interested to hear your updates here. But I guess eventually, say for example, some of the cores we're working on the power side, myself on Microwatt, we're playing with Skyward 130. I mean, eventually we'll have the ability to configure reasonably interesting register files. I mean, at the moment we're using 1 write, 3 reads. Would it be
that's the native cell we're building? Yep.
Oh, great. So you can basically build it up directly.
Yeah. That's what you can build that up without any fancy clocking. The native cell is that cell. That cell is that cell. So that can be run at high frequency and doesn't require much effort at all.
Okay, that's good. We need actually 3 reads, 1 write, so we'd have.
Okay, so you just
double it.
Give you another. I can either give you one of them late with some clocking, or I can give you a second copy. It is your choice. Again, the whole idea here is to have the type of negotiation we're having now, rather than it's too late. You didn't ask for it the day we started, correct?
Yeah, makes sense. And from our perspective, probably just doubling it's good enough. I mean, at the moment we're using
or if one of them can be late, if one of them can be late, it doesn't take any area. It depends on what you want.
Okay, that's good. Yeah, I mean, we're pretty keen because this is one of the last kind of issues we're struggling with the Skyward 130.
This is really we're very eager to have this sort of stuff, so to have users look at it from that perspective. You can see how this is, again, trying to really orthogonalize and simplify and take out the black art. Do you agree?
Yeah, absolutely. And I mean, that's one of the reasons why we're still using all this flip-flop based, even on
yeah. I am hoping that whole bridge design method with flip-flops is gone.
Yep, sounds good.
Sorry to use that analogy, but I think it's a good one. Just a different, this is just a cleaner way to do it. We don't know what the bottom size is you can build, but certainly 32 regs, I can go down to 32 and maybe even smaller and still be a lot more efficient than flip-flop based.
Yep, excellent.
Sorry, I would have taken more, but I thought this was the right amount of detail. The rest of this is quite a bit more, quite a bit deeper into the design. Any other questions? And Anton, be just happy to contact us and just encourage this.
Yeah, absolutely. Early morning here dealing with a kid. Yeah, absolutely. And yeah, I mean, we're just re-engaging on some of this, the Skywwater 130 stuff. So would absolutely be interested
absolutely,
in
absolutely. But the best way to get it to close is to have a customer say they want, and it'll probably help you on lots of parameters, probably quicker and more wireable, because the 130 is is pretty light on wires, right?
Yes. Yeah.
It's okay. The price is exactly right.
Exactly.
No, but let's be honest. The real price is the wall clock time. It's a lot faster, right? You get the silicon quicker because there are less layers of metal to produce.
Yeah, I guess that's true. Yep.
Yeah. I mean, that's different than, can we get the money to build the expensive masks? Fewer layers of metal means much faster turnaround, mean much more experimentation, means learning more.
Yep, absolutely.
Okay, and I see Bill put the Git repo out there on the chat.
Okay, so I actually believe that I will send if you're going to put a formal copy out, I think I'll stop at the chart I did, if you can, because the stuff on the backup, I just assume leave out. Is that okay?
Yep.
Okay.
Yeah, just send James the.
I will be happy to
want.
send you one, because this goes into a lot. It's much too much. I may throw that one in, but I think that's the only one that out of this whole back end of the thing that isn't far too much detail. Right. And because the point of this is that the architect doesn't need the detail. And that's why you commissioned me to look at this, right? Like Mindy?
Right.
Right.
And
right.
also I'd say, yeah, so I have it in chat, the link, and I added it to the description in the Slack channel, but also we have some of these docs in the repo, so we got the details.
Okay. Yeah. But I'll give you the more formal one that I think I'll give you that. I'll give you that what I consider the right formal one.
Sure, we'll add it out there.
Great. Thanks.
Okay, I think without any other questions, we're done here, but it's good. We'll have this as a recording, Bob, for others to be able to listen to.
Great. I hope this was what you wanted. It's good to. I think it's good to get it out and to say it, not as oh my God, we're building something, but why are we building it? Right.
Right. Absolutely. Okay. Thanks, Bob.
Thank you. Okay.
Thanks, Bob.
Thank you very much.